we are going to talk about ionic compounds and covalent compounds. So if we take a look at the ionic compound notes, we're going to review here at the top. So an ion, if you remember, is an atom with a charge. We've been talking about valence electrons, which are the electrons in the outermost energy level. And these valence electrons are what allows these elements to bond and to make these chemical compounds. So in order to recognize an ion you're going to actually see something like, let's use sodium for an example. So Na plus. If you see that plus or a minus sign at the top of it, then that means that it is an ion. So we could also have Cl minus as well. Now, what is going on with these is that if it has a Na plus, that means that an electron has been lost. If you remember, electrons are negative charges. And so when you lose a negative charge, you lose an electron, you're going to have more protons, and protons are positive. So that means the atom or element is going to be overall positively charged. The opposite is true with the chlorine. So if you add an extra electron, then it's going to have a negative charge because electrons overall are negative. Cations are simply atoms with a positive charge. So the good example of this is the Na plus that you see at the top. You're going to be able to recognize it by that plus sign, that positive. Now, this could also have a number with it. So like it could say Na plus 2 or Na plus 3. That's just telling you how many electrons that this particular element has lost. Anions are atoms with a negative charge. So that good example would be Cl minus. So if you see that negative charge or that minus sign, then that means that it is an anion. And I always think about like cats. If you're a cat person, cats are positive. And anions, I usually replace that A with an O because I'm not particularly fond of onions. And so I say onions are negative. So that's how I remember those. It doesn't matter how you remember them. If you want to come up with your own way, that's perfectly fine. The part of the atom that's responsible for chemical bonding are the electrons, as I mentioned earlier. In particular, those valence electrons, those electrons in the outermost shell. Remember, atoms want to have a full outer shell. So if their outer shell's full, like in the noble gases, group 18 on the periodic table, then they will not make compounds. If they are not full, like all the rest of the groups, then they will make compounds. So a chemical bond is just the force that holds atoms together. This is what allows them to chemically combine and make compounds. That is the bond or that force that's in between them. So let's go ahead and take a look at an example here. A very common example is table salt. By themselves, Na or sodium and chlorine are not safe for you to ingest. Okay, you cannot eat those. However, once they chemically combine, they neutralize and they make a neutral substance called table salt or sodium chloride. So when we're looking at sodium on the periodic table, so if you take a look at that on the periodic table, its atomic number is 11. So that means it is going to have 11 protons and 11 electrons. Now, there's not a plus up here, there's not a minus, so it's going to be neutral. So here in the middle, in the nucleus, I'm just going to put my protons. I'm not going to draw all those out, but we are going to put the protons are equal to 11. So that means our electrons are also 11. So we're going to draw those in the shells. Remember, the first shell can hold a maximum of 2 electrons. So there's 1, 2. Second shell can hold a maximum of 8. So 1, 2, 3, 4, 5, 6, 7, 8. That makes a total of 10. So that leaves us with 1 electron in our outermost shell. So sodium, or Na, has 1 valence electron. Chlorine, on the other hand, if you look up chlorine on the periodic table, its atomic number is 17. So its amount of protons are going to be protons are going to be 17. The electrons are also 17. Okay, so chlorine has 17 electrons. So we're going to go ahead and go to the first shell. Put 2 in the first shell. Second shell will hold up to 8, so I'm going to go ahead and put 8 there. And it's a lot easier for me to draw just little dashes on this computer, so that's what I'm going to do. So that's a total of 10, and then the last shell is going to have 7. To make 17. So Na only has 1 in its outer shell, 1 valence electron, so it is not full. It has 2 choices. It can either get rid of the 1 to make the second shell the outer shell and it be full, or it can gain 7. They always go for the easier option, so it's going to try to get rid of that 1. Chlorine has 7 and only needs 1 more, because remember 8 is full. So it's actually going to get that 1 from sodium. So sodium is going to transfer over its electron to chlorine. So that makes it 10 electrons because it gave 1 away. And now chlorine has 18 electrons. So because the sodium lost an electron and now has only 10 electrons, that means the protons, which are positive, there's more of them. So overall, sodium is going to have a positive charge now. That's what makes it an ion. Chlorine, because it gained an electron, now has 18 instead of 17. So it's got more negative charges than positive charges. So now it becomes negative. So now chlorine is an ion. Now opposite charges attract. So these two elements are going to move towards each other. They're going to chemically combine. And when they chemically combine, they're going to make NaCl, which is table salt. Because they have opposite charges and there's only one each, they're going to neutralize each other. So now you've got a neutral element, or neutral compound, a neutral compound of table salt. So to summarize, sodium gave away an electron to chlorine. Sodium became positive. Chlorine became negative. And this is an example of an ionic compound. Ionic because, again, ion means an atom with a charge. So now this compound is ionic. Now, some properties of table salt that we can use to help identify ionic compounds include the following. So when you think about table salt, you know, it's easier to think about something you already know, you've already seen before. So if you're thinking about what properties do ionic compounds have, think what does table salt have? So if I were to hold table salt in my hand, it would not melt. I'd need a much larger amount of heat in order to get it to melt. So we say that table salt has a high melting point. It needs a lot of heat in order to melt. So in general, ionic compounds have high melting points. So table salt is also a solid at room temperature. So in general, ionic compounds are solids at room temperature. If we were to put table salt in water, it would dissolve. So ionic compounds tend to dissolve in water. And it conducts electricity when it's dissolved in water. So ionic compounds in general tend to conduct electricity when they dissolve in water. Now, if you look at the periodic table again and find where sodium is and where chlorine is, sodium is a metal, chlorine is a non-metal. So ionic compounds typically occur between metals and non-metals. Now remember, metals are found to the left of the metalloids or the stair-step line, with the exception of hydrogen, and non-metals are found to the right of the stair-step line. If you think back to sodium and chlorine, sodium lost an electron and became positive. Chlorine gained an electron and became negative. So ionic compounds will gain or lose electrons. So that's another way that you can identify them. Now let's talk about covalent compounds. Covalent compounds are pretty much the opposite of ionic compounds. Covalent compounds are going to occur when atoms share electrons. Where ionic compounds give or take, covalent compounds share them. We're going to look down here at water, and then we'll come back up to part B, but we'll look at water as our example of a covalent compound. Okay, so hydrogen has an atomic number of 1, so that means it has 1 proton and 1 electron. So I'm going to draw 1 electron here. And I'm going to draw it to where it's overlapping the oxygen, and you'll see why in just a moment. So on this side, the hydrogen also has just 1 electron. We'll draw it to where it's overlapping as well. Now, oxygen, its atomic number is 8. If you look on your periodic table, so it's got 8 protons, 8 electrons. Okay, and so we're going to draw its electrons. So 2 go in the first shell, and 6 are going to go in the second shell. So 1, 2, 3, 4. Now here's where the covalent compound part comes in, where they share the electrons. So it's got 4 in the outer shell. We need 2 more. So we're going to place it to where it overlaps with hydrogen. Because if you remember, hydrogen only had 1 valence electron, but it needs 2 in order for that outer shell to be full. So if it shares the other electron with oxygen, then that outer shell is going to be full, and it's going to chemically combine to make water. Now, covalent compounds, again, they have the opposite characteristics of ionic compounds. So when you think about covalent compounds, think about water. So if we have frozen water or ice in your hand, you're just holding it there, it's going to melt, okay? Because covalent compounds or water have low melting points, where ionic compounds have high melting points. So it's the opposite. Where ionic compounds are typically solids at room temperature, covalent compounds are usually liquid or gas at room temperature. And where ionic compounds typically conduct electricity, covalent compounds tend to be poor electrical conductors. They don't conduct electricity very well. Now again, these are just general characteristics. It's not going to apply to every single covalent compound out there, and it's not going to apply to every single ionic compound out there. So let's recap before we move on to isotopes. So ions have different numbers of electrons. Protons do not change because they are the identity of the element. So that leaves us with the neutrons. So when we look at an isotope, the definition for an isotope are atoms with different numbers of neutrons. And neutrons typically have an atomic mass of 1, just like the protons. So in order to get the mass number, we would add our protons and our neutrons. But because the number of neutrons is different, that means the mass number will also be different for those elements. So some examples of what isotopes look like and how they can be written. So I've got carbon on here. It's got 3 isotopes. We've got carbon 12, carbon 13, and carbon 14. So if you notice, your element is written first, followed by a dash and the mass number. So 12 is going to be the mass number, 13 is the mass number, and 14 is the mass number. Okay, so these are 3 different isotopes of carbon. They're also carbon, same number of protons. There's not any plus or minuses, so that means they're not ions either, so they're going to have the same number of electrons. But their neutrons and their mass number is different. So if I wanted to find the number of neutrons for carbon 12, I'd look on my periodic table. Carbon has an atomic number of 6. So I would subtract 12 and 6, and that would give me 6. So there would be 6 neutrons for carbon 12, 7 neutrons for carbon 13, and 8 for carbon 14, because you're just subtracting the atomic number and the mass number. Now, isotopes can also be written to where they have the chemical symbol, and on the left-hand side at the top, they're going to have the mass number. So this 12 represents the mass number, and number 6 represents the atomic number. And it's going to be on the left-hand side at the bottom. And so you can also have, for example, you can have an isotope that is also an ion, because it can have different numbers of neutrons and different numbers of electrons. Remember, they typically become ions when they're trying to chemically combine with something. So if we look at carbon on the periodic table, carbon is in group number 14, which means carbon is going to have 4 valence electrons. In order to be full, carbon needs 8 valence electrons. Okay, and so it's either going to get rid of the 4 that it has, or it's going to try and take 4 from another element. So depending on what element it's combining with, this could either be a -4 or a +4. But this is also an isotope that happens to be an ion, so you can see those negative numbers as well.